Hi everyone, welcome back. This is our last section of chapter 12 about three-dimensional volumes and surface areas. So this is about spheres. And so we're going to look at some formulas for finding surface area and volumes of spheres. So just in general, we haven't really talked about spheres at all, but you guys probably have lots of experience with them. But the most common definition would be the set of all points in space, three-dimensional space, that are equidistant from the center, which could be any point. When we were talking about defining circles, we defined them pretty much the same way, but in two-dimensional space, so in flat space. But just like we did with circles, we can talk about all these different parts of a sphere, and they mean basically the same thing. So we can talk about the radius of a sphere being the distance from the center to any point on the outside. We can talk about a chord being any segment that touches the sphere in more than one place. We can talk about the diameter being a chord that passes through the center of the sphere. So all of those terms still mean the same things that they did when we were talking about just flat circles, but now we're talking about three-dimensional spheres. And I would say that your most common experience with a sphere would be like with a ball. So the first formula that you'll see that is related to spheres is talking about finding the surface area of a sphere. And so you can kind of think about like unfolding the covering on a baseball when we're thinking about finding the surface area of a sphere. And so if you think about what that covering looks like when it's totally unwrapped, it kind of makes these four circles that then cover up the ball. And so the formula for the surface area of a sphere is 4 pi times the radius squared. And remember, pi r squared is just the area of a circle. And so if we're thinking about a sphere, it's just 4 of those circles. So let's look at a practice problem. So if we look at this sphere, and we're going to try to find the surface area of it, we know that the surface area is equal to 4 pi times the radius squared. And so when we do that out, this is what we get for the surface area. When we're trying to find the, great circles. So this is something that's very specific to spheres. It doesn't have anything to do with circles. So if we think about a plane intersecting a sphere could cut it in lots of different ways. But there's one particular type of intersection of a plane and a circle or a sphere that's called a great circle. And a great circle is when a plane intersects a sphere and creates two congruent halves to the sphere called hemispheres. So kind of like the equator of the Earth, a great circle is any place where a plane would intersect a sphere and cut it into two equal pieces. So if we're looking at volumes of spheres, the volume of a sphere is equal to 4/3 pi times the radius cubed. Remember that whenever we're talking about volume, we're talking about a cubic unit. It's a three-dimensional unit. Again, r is the radius. And so if we think about finding the volume of that sphere we were looking at in the surface area example, it had a radius of 8. So if I plug that in, I can say 4/3 pi times the radius cubed is 2,144 inches cubed now, because we're talking about volume. And so here's one more for you to see, just another example. This is a soccer ball now. It has a diameter of 9 inches. Oh, and I just noticed I made a mistake. So if they're telling you it has a diameter of 9 inches, in here shouldn't be the diameter. It should be the radius. And so I'm going to come in here and exit out. So this should be the radius. So that would be 4.5, right? And so if I just throw that in my calculator really quick, we'll go 4.5 cubed. And then times pi times 4/3. So this actually ends up being 381.7. And it's still inches cubed. But so you can see that, like, while these problems are pretty straightforward, you do have to pay attention to like what you're given in the problem. So the diameter is 9 inches. The diameter is this distance, not the radius, right? And so if the formula wants you to use the radius, make sure you use the radius. All right. So last thing is just looking at one of these composite shapes. This one is like an ice cream cone. So take a second and see if you can figure out the surface area and the volume of this ice cream cone. You can pause and then just come back and check your work. And if you look at this, so if you look at my work down here, you'll see that when we're finding the surface area of the cone here, we really only need the lateral area of this cone, because this circle is inside of the ice cream cone, so we don't need to know that area. So when I found the surface area of the cone, I just found the lateral area. That's why it says lateral only here, and that's pi RL. So again, in this one we had to find the slant height, L, using Pythagorean theorem. So like right in here, so it's a right angle. Right here, I just pulled that out, right? So this length, this distance there is 10.8 when I use the Pythagorean theorem. And so that's what's going in my surface area formula to find the lateral area of that cone. And then again, to find the area, the surface area of this hemisphere, this half sphere that's on top of the cone, I'm just using the formula to find the surface area of the whole sphere, but just multiplying by 1/2. And so then I find that the surface area is 236.2. And then the volume, same thing, finding the volume of the cone, using the formula for volume of a cone, 1/3 pi r squared times the height. And so I get 167.55. And then to find the volume of the hemisphere, this top part of the cone, I'm going to do 4/3 pi r cubed, but then multiply 1/2. It's only half of the sphere. And then when you add them together, this is your volume. So that's it in this section. It's pretty straightforward. But again, make sure that you're writing down questions that you have as you go through your homework. And we will talk about them in class. I hope you guys are having a great day.